Okay, so to think about this snowball thing, what was the problem was phrased as snowball volume, rate of change is proportional to surface area? Yeah? Okay, so that's telling you about, and some of you guys were having confuzzleness with this thing, because you're really thinking like V prime, right? Which is not a particularly bad idea. And is proportional to means there's some constant, right? And then here I should put surface area. The dorky thing about surface area is that it's also V prime.
Oh, yeah, yeah.
The problem is just that these are different derivatives. The rate of change of the snowball's volume is dV dt, right? And the surface area is dV dr.
That's a thing?
That's a thing. Yeah, so if you don't know this, if you still have the formulas, right? So the formulas are volume is 4/3 pi r cubed, right? If you differentiate volume, you get 4 pi r squared, right? Which is the surface area. And the reason it's the surface area is if you think about having a sphere, right? If you make it just a little, like if you just pop the radius just a little bit, how much volume do you get? Well, if you think about peeling that little skin off, right? It's like the radius of the sphere thick, or the change in radius thick, right? And then how big is it? Like what's the area? The area of it's basically the surface area of the sphere. And so really you get that the rate of change of volume is the surface area, right? Because like the change in volume is the surface area times the change in radius, so you divide the change in radius to the other side, and you get delta V over delta R is basically surface area. That's kind of where this formula comes from. That's true of spheres in general. So if you found the volume formula for the 7-dimensional sphere, to get the surface area, you just differentiate it with respect to radius. I have no idea what that would mean, but that's how you would get it, at any rate. This is true for at least in 2D too, right? Pi r squared, and then the circumference is 2 pi r.
Yeah, I haven't noticed that.
It was really cool to watch a couple of you guys like fiddle with these, like after I gave you one formula, you noticed the other one, and you're like, shit. So if you notice this, right, then how do you rearrange this guy to get the rate of change of the radius? Oh yeah, sorry, that was the rest of the problem. Show the rate of change of radius is constant. So to show that this is constant, you just multiply both sides through by, how about 1 over dV?
Fair enough.
Right? How about multiply both sides through by dr over dV? Yeah, really that's kind of using the chain rule.
This kind of stuff.
So you get like dr dV times dV dt is some constant k. And by the chain rule, this thing is dr dt. Alternatively, like you could take these formulas over here and be like, okay, so the rate of change of the volume is ddt of 4/3 pi r cubed. right? And that's supposed to equal some constant k times the surface area, which is 4 pi r squared. Right? And then you know how to actually differentiate this thing with respect to time. You get 4/3 pi, oops, not 4/3 pi r cubed. Why not? Why isn't this thing constant? Oh yeah, there's no time. Well, so what's changing with respect to time? Is 4 changing with respect to time? No? Is 3? No. Is pi?
No.
Probably not. Is r changing with respect to time? Yeah. Oh, so I needed the chain rule here, right? Because r was a function of time. So I need my 4/3 pi, but then r is a function of time, so I get 3r squared times dr dt. And that's k times 4 pi r squared. And then you can like divide by a bunch of shit here. Right? Like, the 3's cancel, the 4's cancel, the pi's cancel, the r squareds cancel as long as r is not 0.
Wouldn't have a sphere.
Why am I assuming r isn't 0?
Because you wouldn't have a sphere.
Yeah. Because what's the point in talking about the snowball that isn't? Right?
That sounds awesome.
Cool. So, either way, I just thought this was a cool, like, this was a neat thing to notice.
Yeah. I kind of.
Yeah, if you didn't notice it though, like, you can do this with the formula.
Kind of noticed adjacent.
If you noticed r was changing with respect to time. If you didn't notice that r was changing with respect to time, then what the heck is the rate of change of the radius? Well, it should be 0, right? But of course, then the volume isn't changing. That's weird.
I just couldn't.